All right. So today we have the pleasure of hosting Bram Vanhecke, who's going to be talking about AI and tensor networks, a love affair. Wonderful title. So Bram is a postdoc at Uni Wien, I hope I pronounced that right, in the group of Norbert Such, and he works on tensor networks and branches out to some machine learning applications. So previously to that, he worked on tensor networks, specifically PEPS, at the group of Frank Verstre, and before that, he was at Q Leuven. So the floor is yours, Bram. Enlighten us.
Thank you very much. It's a very nice introduction. I feel like I should maybe correct the pronunciation of some names just for their sake. So it's Norbert Schuch and Frank Verstraeten.
Thank you. I felt like I might have done a couple mistakes there.
It's quite okay. Okay. So yeah, indeed, the point is to talk to you guys a little bit about tensor networks and machine learning and how they connect, specifically in two kinds of ways, with two papers that came out, I guess, relatively recently. One talking about using tensor networks for some machine learning application. So that's sort of the love going in one way. And then one where we use some machine learning insights and tools to better do our tensor networks analysis. So that would be the love going the other way. So it's, yeah, okay. So with those two things, I'll be keeping it relatively superficial, but feel free to ask any questions that you might have, interrupt. I don't mind. First, a shout out to the collaborators. Can you guys see my mouse? You can nod. Okay, good. So over here, that's Anna. She's a postdoc at Uni Wien, together with myself, and Norbert Schuch, who's the big boss over there. So we did the tensor network stuff together. And then there's Samuel Wautier, who's also in this talk. He's essentially here to answer any and all active inference questions that you might have, because this is for sure not my my field of expertise. He's from Ghent, working in the group of Bart, Dont, and Tim Verbele is a postdoc also in Ghent. Yeah, so that's the team. So first we will discuss MPS and how we use it for active inference planning. I will give some sort of a basic introduction to active inference, what it is, where it comes from, and then how we use an MPS. And then later, automatic differentiation. So that is the essential, the tool of the machine learning community that we so learn to love. But it has been somewhat misused in tensor networks. So there have been some flaws in its application. The problem essentially being that it's a black box, and there happens to be a full-on mistake in this black box, and it led to years of people just not knowing why things were not working out and misdiagnosing the problem, and then we solve all of the problems. Yeah, so that's something to look forward to. Active inference. Okay, so I'm not going to talk about any of the details on this thing. It is essentially a means to model an agent, more specifically a biological agent. So how does a logical being, how does a biological being plan and act in the world? So it is used kind of to understand psychology. So you have these mathematical quantities. So it's really like a mathematically rigorous model based on Bayesian statistic, Bayesian logic. And you can really connect the mathematical quantities that you end up putting in your computer and connect them to particular parts of the brain. And some people can get really concrete with that. So there's computational psychology that is now a thing, apparently, that you can do. which is quite amazing, and I think a good step for this field to become a bit more predictive. But then you can also take it the other way, and that is what machine learning has often done, saying like, we now learn a bit of how people think, let's make machines think like that as well. And so how can we program an agent to make logical decisions, make proper planning for the future, can also be derived from this study. So let's make it a bit more concrete, but not much. Active inference models the behavior of an agent. This agent can make observations. It's generally done passively, so you just get observations. But it's for sure also interesting to consider that an action as well, where you, because making an observation requires resources typically. It is not a thing that we do, but it might be nice to make that a thing as well, to say like, I wish to make an observation. That's an action as well. And actions. So you look at the world in some sort of a very limited kind of way. There's a certain set of observations you can make. There are certain actions you can undertake as an agent. And then you plan to minimize surprise. And surprise is this, it's a bit of an abused word. It captures essentially all goals. So if you wish to not be hungry, then you're kind of, this is phrased as saying you're surprised that you're hungry, right? So you would plan ahead such that you would not be hungry, or in other words, you would plan ahead such that you would not be surprised about your hunger. And it's a word that has more mathematical meaning, but so that's the kind of how you're supposed to think of this. To make these actions, to do the proper planning, and this is a crucial part of the active inference insight, is that you need some sort of a model of the world. You need to be able to run a crude simulation of the world in your head to be able to predict what would happen with certain actions, such that you can actually do this planning. Now, to have this imagined model of the world, you need more degrees of freedom, let's say, than your observations typically give you. So you may be able to, let's say, look around the room, and you want a book to read, but this book is not in this room, it's in another room, the door is closed, you cannot see the book, but you should know that the book exists. If you step outside the door, you should know cars are there. They are a variable. The stuff that you cannot not observe should still be included in the dynamics. Okay. Which it all sounds obvious once you say it, but it's important to really start modeling this stuff. Yeah. So this model of the world is fine. It can be imperfect, and it should in principle be updated as time goes by. And as you're starting to, in psychology or with animals or whatever, you try to understand how do they learn, how do they update their model of the world. That's sort of a part of active inference that's looking at this feedback loop, like how do you improve your general understanding of the world to then be able to make better actions. However, this is a part that we are not interested in, because this model of the world will be the machine learning part. This will be the thing that we just machine learn or fit, right? You just fit the world, kind of. Typically, this is represented with a partially observable Markovian decision process with a neural net in there. Yeah, but we will not obviously do this. We will replace the model of the world with a tensor network. And we will discuss the differences, the benefits, the changes that makes. So a very basic example, but not so basic that we can actually solve it. So we didn't do this one. We did something even simpler. So there's a car. This car is the agent. It can make observations, namely the position. And it really wants to get to the star. So this car is deeply surprised that it is not at the star, and it wishes not to be surprised. Hence, it will move its way towards the star. It can also undertake actions, such as pushing to the left or to the right. I'm sure you guys know the mountain car thing, right? So it can push to the left and to the right. If it pushes to the right, it cannot push all the way up the mountain. It will have to sort of oscillate back and forth until it gets to the star. And hence the planning is somewhat more complicated. Yeah, so it's an interesting model to test stuff on. The hidden variable in this case would be the velocity. So you cannot observe the velocity, but clearly you do need the velocity to be able to make proper predictions. So the Newtonian equations, there's second order differential equations. The position is not enough to integrate to the next time step. You need also a velocity. So this is the thing that you will have to keep in your mind as a thing that you cannot see, but that does exist and that is necessary to have a proper model of the world running in your head. Okay, agents is surprised. This surprise is modeled with a preferred distribution. So everything in active inference, like I said, it's a Bayesian statistics thing. It's all about probability distributions and evolving probability distributions. And saying I want to go to the star is having a preferred probability distribution of an observable. Namely, okay, I want to observe myself around the star. The cost function that you use to do that is the expected surprisal, which is where this surprise word comes from. This just is the thing. That's sort of the result that comes out of the active inference framework. It tells you if you are able to run a proper, reasonable simulation in your head of the world, and you can use it to make this, to calculate this number, the expected surprisal, after a certain set of actions, a given set of actions, what is my probability distribution of my observations, and then calculate the expected surprisal. If you can do that, then you can try to minimize that so that you're not surprised. Right, so this is the goal. You want to be able to calculate this thing for given actions. And then finding the actions is a matter of optimizing this number. So we will not concern ourselves with optimizing this number over the actions. That is a thing that we will just copy over from previous work. It's essentially a search tree. What we will occupy ourselves with is, can we calculate this number? Because already the Markovian decision process can technically not calculate this number. They can calculate an upper bound to this number. It's technically, this thing is not accessible. But of course, they have an upper bound, so it works reasonably well. But we do have this number, and that's kind of pleasing. That's a first difference. The Markovian decision process has a function, right? A neural net that takes the position that you measured, the action that you did, and your hidden variable, which should start to become essentially representing the velocity, and spits out a new internal state. And there's some other things that you have to optimize, essentially maps from this internal state to observables. But that's essentially how it works. We will not do that. We will construct a tensor, of course. And this tensor represents a probability distribution over all the possible observations, all the possible actions. Clearly, in a deterministic world, it is just a tensor full of zeros and ones. All the observations and actions that are allowed by the dynamics, okay, that's probability 1, that this sequence of observations and actions follow each other. Those that are not allowed will have 0. But inherent in this formalism is some noisiness. Your observations might not be exact. your actions might not do exactly the thing that you want to do. You want to be robust against noise. Yeah. So in general, so a probability distribution given by over all of the possible observations and actions. We optimize this, and then based on this, we can clearly calculate this number, because it's just a matter of fixing the actions and then calculating the reduced, I guess, reduced density matrix, the marginal probability distribution over this observations that you're interested in.
I had a quick question actually about this this quantity here. Just the bracket. It means expectation, right? Okay.
Yeah.
And so this thing is like the entropy, right? So the expectation of minus log. Is it the same thing, or?
It's similar to an entropy, but not really. So the PO is the preferred distribution. So if P was the actual probability distribution, then this would be the entropy.
Okay, so it's more like a KL or something like that.
It's very much related to this DKL. It's
okay.
Exact relation, I cannot tell you, but it is from there that it comes.
And so can you clarify, like this was kind of my point, like the expectation is taken with respect to which distribution here?
Of your internal model.
Which is not the preferred distribution. Okay.
No, the preferred distribution is some God-given, it is your preferences.
Okay. Okay. Thank you.
This is how this is encoded. Like every agent has this inherent desire, which is encoded in this P.
Okay. Makes sense. Thanks.
Thank you. Please, don't hesitate if anyone else has a question. Oh, is there a chat question? I'm sorry. Okay, I will notice sooner if there is a question, but you can interrupt. Okay, some tensor network preliminary, but I gather that is not super necessary. Generally, big tensor, exponentially many variables required to specify it. So it's not actually practical to work with that. The whole point of tensor networks is a lot of tensors have this structure to them, encoded in the entanglement. But really, it's just a matter of how are the correlations in this tensor, and if there are enough correlations, then you might actually be able to decompose it in some efficient way. And there have been a couple of machine learning, like tensor network applications in machine learning, where this was not at all well motivated. Like if you try to do MNIST with MPS, there's no reason to expect the tensor that captures these images to have this nice structure of an MPS inherent in it. So this would be a location where I would intuitively think MPS is not really the right thing to do. You're not going to get all that much benefit out of doing this MPS. But this right now does have this benefit, because you have this clear time orientation where observations, like with this velocity, you go 2 steps back. 2 observations are enough to determine the velocity.
Sorry, Bram, I have a question.
Please.
So yes, it's not applicable for MNIST, because I think that if I'm wrong, please correct me, because the data set is small. So if we have the larger data set, so I think the MPS works well, no?
So okay, so for sure they can make the MPS work by pushing the bond dimensions high enough. So any tensor can always decompose into an MPS. The question is it efficient? Meaning, are your bond dimensions very low? Can you somehow get by with very low bond dimensions?
Exactly, yeah.
And MNIST has you're trying to capture a thing that clearly has 2D correlations with a 1D thing. Now, any 2D thing, you snake through it, it's kind of 1D, but not really. The thing to use for MNIST, and this has been done, would be a PEPS. So you can do an MNIST machine learning thing with a PEPS at bond dimension. I don't know what they did, like 3 or 4.
The 2-dimensional network, okay.
Yeah, so it's much more efficient, much more effective. Far fewer parameters are needed.
Thank you.
Yes. So whenever you do so MPS are overused because they're very, very practical. So it's just stupidly easy to use them for MNIST, and it's hard to use PEPS. But from a research perspective, it's clear one is more efficient. Fundamentally, you will be able to, if given better tools to optimize stuff, this will be the thing that gives you, in the end, the better result. At this point, you may not have them, but in the far future, that's where this will end up. Which is just to say that this is a case where MPS is actually correct to apply, because here you have time, you have short in-time correlations, right? Just a couple of observations in the past should be enough to determine your hidden state. Your hidden state, by the way, is should be thought of as your virtual dimension. So the bond dimension of the MPS becomes the hidden state, and it's essentially a quantum state. So our hidden state becomes a vector in some d-dimensional Hilbert space, and evolution of the hidden state is acting with an operator on the hidden state vector. And so you have this nice thing where you kind of make things quantum mechanical. So it feels more potent. Though, yeah.
Do you mean, sorry to interrupt, but do you mean that you were enforcing some unitary constraint on those core
No.
tensors?
It's not
okay.
it's not a unitary evolution. This
Okay.
would be nice, but it's not.
Okay, thanks.
Yeah, no. Everything is kind of completely let loose. So everything is completely free, optimize away.
I see. Thanks.
Okay. So MPS should be very usable in this particular instance. So now let's go to the actual model that we studied, which is this. So again, it's a benchmark. It should be clear. We're definitely planning on doing this on a more interesting setting. But it's just a first check where we essentially try to see, can we replace the existing neural net infrastructure with this probability distribution given by an MPS. Like, we have very good reason to think that it can be, and it can be very, very efficient. All the reasons are there. Let's just see. So that's the goal. So there's a mouse. The mouse wants cheese. It is surprised that it is not having cheese right now. And there's a hint. There's this arrow. It can go to the arrow and then see where the cheese is. So what you want it to do is go to the hint and then go directly to the cheese. If it would not go to the hint and directly sort of make a guess, then still it would be quite surprised, right? There's a 50-50 chance. So if you get the cheese or you don't get the cheese, there's still some surprisal there. Yeah, so that's a simple model. You train this by generating a bunch of consistent data. It should be easy enough. So this is a list of observations and actions that are consistent with this world. And then we maximize the overlap of an MPS with this data. Yeah, so you can imagine the MPS that just has this maximal overlap that will just capture the probability distribution from which this data was generated. We do this using a two-side update, which is a nice thing. I'm sure that you guys have heard of. You essentially do a gradient descent of your tensors, but before you do the gradient descent step, you group two tensors together so that they become one slightly bigger tensor. And then you take your gradient descent step, and then you split them up again. But in this process, the bond dimension may have actually changed. And so you can learn what the appropriate bond dimension is. Yeah, all of this stuff is extremely well understood since the 90s. It's just TNRG, really. And the first nice result that we get, which is very pleasing to us, is that the bond dimension first goes up. Yeah, because at that point you're still noisy, you haven't learned all that much. This clearly is like an overfitting stage. But then as you get better and better, the model actually learns that it doesn't need that much bond dimension, and it cuts it itself. It just dynamically figures out, it streamlines its own thought process in a way. and gives you a smaller bond dimension, which, yeah, like if you imagine if you had done a similar kind of a thing with a neural net with like 5 layers, you're never gonna dynamically figure out, I actually only need 4 layers, you know, something like this. But this thing can just tell you, actually, I don't need all of these resources that you're giving me. I can do it with less, which is nice. Yep. And then we get the result. Right. So the x-axis is the value of the cutoff. So at every 2-site update, you fuse 2 tensors, you take a step, and then you cut it up again. This cutting process is done with a singular value decomposition. And you have to decide, okay, what are small enough singular values for me to throw away? That's the cutoff. And so you can clearly see if you're heavily throwing away, then you're not going to be very accurate. And so you see, for a large cutoff, it's not properly learning the dynamics. But then as you decrease it, at some point you do reach a point where from then on you just always find a good enough distribution to do the planning with. Also, you can see that you need just a big enough data set. With a too small data set, you're also just not going to get there. Okay. So that's the active inference part. Am I good to... Oh, I guess there's an outlook. Okay, so we want to do more complicated models, as I said. Infinite horizons, that's a thing that's exciting us very much now. So there's no reason to think in this, because it's in this time evolution thing, that a very large, like an infinite tensor can also not be very well approximated with an infinite MPS. And so we know very well how to work with infinite MPS. That's a completely understood thing. And it will allow you to train just 1 tensor, right? So now with the T-Maze, we trained 3 tensors, when really you should be able to, like, that this is clear, right? There's the dynamics of the world, and it's completely capturable in principle with just 1 tensor that takes your virtual hidden state and evolves it according to observations and actions. And just 1 thing that gets you there. But it's a bit different to optimize. So the DMRG thing changes quite a bit. But yeah, that should be cool. So we're excited about that. Also, it would allow you to do arbitrarily long planning, you know? Continuous variables are a bit of an annoyance. So clearly all these tensors, yeah, an observation, all of these things are assumed to be discrete and therefore easily encodable into a tensor. Continuous variables are not easily encodable into this inherently discrete tensor, but there are techniques out there. There's some very nice work happening where people are using tensor networks, specifically MPS, to simulate the Navier-Stokes equations, and they have a very nice, elegant encoding for mapping continuous variables into this discrete thing. That seems to be quite a bit more efficient than something like some, you know, basis in L2 that would also work. So yeah, we're excited to try some stuff there. And also the planning. That's actually a thing that we should be able to test that pretty soon. The planning part right now is just taken over from previous work. So we didn't do anything with the planning part. But as I said before, it's just minimizing the expected surprisal. That's another variational problem. Surely you can do this with tensor networks as well. And that would be very good, because the planning right now is done with a search tree, and it's really quite time consuming. So if we can do a tensor network improvement there, that would be nice. And we think it's reasonable. Yes?
Yeah, I have a couple of questions and comments. One of them is, I had a question about your tensor that you parameterize as an MPS. Do you consider that its component is the probability, or do you take the square like in the Born rule? Like, what is the probability? Is the actual entry, or do you actually use the Born rule? Basically, is my question.
We use the Born rule. We do quantum probabilities.
Okay, because then it's yeah, okay, that's interesting. And so when you get to this infinite horizon, so you have this translation invariant systems, and basically this is very closely related to HMMs, right? So HMMs are very similar to that. I don't know if you know these connections.
I can Google HMM.
Hidden Markov models. So basically, you can think of HMMs as this MPS, but you don't use the Born rule, you don't take the square, and instead you constrain the components of the core tensors to be positive. Basically, you have a result that shows those are equivalent. And HMM, in the world of reinforcement learning, I don't know if you heard about predictive state representation, but there are basically HMMs used in the context of reinforcement learning, which is very similar to what you're doing to the modulo of the Born rule, right? So it's like basically using more the HMM, like you try to constrain your weights to be positive, or even sometimes not. But I think there was a lot of link in there that yeah, I can send you a couple of references here.
I guess we would be interested in seeing that. That's for sure. Definitely. Thank you.
Yeah.
So this kind of question can definitely keep coming.
Now, okay, I have actually, and for the continuous variable, we just have a paper recently out with my former postdoc Jacob and other folks at Zapata, where we basically do some MPS on continuous variable for generative modeling. So I think this is also quite useful here.
Yeah. So so how do you encode these things, or do you not want to say, or it's too long?
No, for the continuous variable, no, it's just on archive, like for 1 week or 2 weeks. It's basically just with the, as we were mentioning, the L2 basis function, right? So you choose a basis of function in L2 spaces, and then you use that as kind of an embedding map to go from your continuous observation space back to something that is discrete. And
Yeah. So we played around with that, but like you can imagine, for example, taking a Fourier basis as good as any, but then after learning, quite a bit, you see that actually there's only a certain subpart, a very non-trivially parameterized subspace and that's the only relevant thing. And ideally we would immediately train for this subspace kind of. So that would be nice.
This is something we actually do. We had this kind of what we call your compression layer, I think, that goes beyond the basis function that you choose and the actual MPS. You have this extra thing that is projecting it down linearly, but which is basically that, right? Additively learning the subspace of the L2 space that you want to. So you can do it like that. And at some point I wanted to investigate, but I didn't do it. But I think you could also kind of pipe this directly with a tensor, with a neural network that is doing kind of the function basis thing, right?
If you would combine things like that, that would be cool.
That could be cool. But anyway, this is more. I let you continue, but we can chat more after.
That would be the epitome of the love affair.
Absolutely.
Okay. Very nice. So, any more questions on the active inference stuff? Very good. You can ask questions more later if you remember anything. Okay. Then the PEPS thing. I don't know if PEPS have been talked about in the past. They're essentially the natural generalization of MPS. So they're a tensor network that is inherently 2D. So this is a hexagonal lattice. What's missing here are physical legs sticking out. So if it's a quantum state, then it should have physical legs on all of these sites. But this thing actually represents a PEPS overlap. So it's psi, sort of the quantum overlap of two of these PEPS states. So two PEPS states with physical legs that are contracted. So you end up with this 2D network with no legs sticking out. And it's actually infinite. So we typically, weirdly, in PEPS, the easiest thing to do is infinite PEPS. Infinite is much easier than finite, which is a bit opposite from MPS. So what you want to do is, the core problem that you have to do anything with PEPS is contracting this thing. You have an infinite 2D network, calculate this or something similar to this. So like, for example, an energy would just change, you insert like a Hamiltonian term over here, and the rest of the network essentially stays the same. So yeah, the core problem is if you're able to contract this, then you can calculate the energy, correlation functions, anything. Right, okay, I said all of it before all of this. Yeah, infinite is really quite strong. It's also hard to work with, so it's really only pulled out in challenging systems. So if you have a sign problem, if your mean field really just doesn't work, you have strong correlations, exotic behavior like topological order, this is when PEPS they start to shine. So you contract this. It's a bit of a mess. I'm sorry to dump it all on you like that. So you contract this. There's several approaches, but this is the CTM. We'll talk about the CTM, which is the industry standard, sort of. So you imagine that you have these green tensors. So T boundary tensors and C the corner tensor, all the way at infinity. So you have this infinite 2D network, and at infinity at the boundary, you have these green tensors. Right? You can put at infinity what you want. Right? It doesn't affect stuff happening in the middle. That's sort of your assumption. And then you say, well, if these green tensors satisfy all of these nice properties, then you could imagine going to the corner, right? So you have this corner, and you can sort of zip it. You change one C into like an enlarged corner with two tensor lines into this, just a corner with one tensor line. And then you can take this sort of zipper tensor, and right, you would put it right, this would be over here, and then this acts on this other green tensor and the PEPS tensor, and you pull it through to the right. Then you see, well, if I can do this once, you can keep doing this. So you push this zipper all the way to the right, and you do the same thing at the other corner. And then with this zipper, you zipper all the way to the left. And when they meet in the middle, you also get this. So this would allow you to essentially shrink your green boundary. You can move it inward each time with these zipper equations.
Oh,
so
sorry.
Yes.
You transpose is the orthogonal basis, something like that?
Yes.
So for C or for T, I confused that orthogonal basis for which of these tensors? So
the way that you get from this equation to this is through an eigendecomposition.
Okay.
Yeah, so the eigendecomposition would have this C being diagonal, and this basis, because this thing is Hermitian, okay, I didn't say this thing is Hermitian. And then this eigenbasis would be unitary, or an isometry in this case. It's a truncated eigendecomposition that gets you from there to there. So you do a rank approximation, a low rank approximation of this thing.
Okay, yeah, thank you.
No worries. So it's a bit of a weird thing to try to imagine, to move your green boundaries in through these zipper equations. This is called sort of a renormalization group, because you're capturing many variables with fewer variables at each one of those steps. The fact that this works is kind of magic. There's no proof of it. But that's the thing that people are doing in their head, and these are the equations that they're solving. And they allow you to move this green boundary all the way in from the, infinity all the way to around something like this, which would be two PEPS layers with a Hamiltonian in the middle. Right, so that's why they're purple. There's a Hamiltonian in there. Yeah, so you find these tensors. Okay, so that's the thing that you want to calculate. That's the energy. So if you have these green tensors, you're very happy. You can calculate the energy. You get these green tensors really by iterating these equations. So you start with some C and some T, As I said before, you do an eigendecomposition of this object, a truncated eigendecomposition, and this updates C, and also gives you these zipper tensors, which are just the eigenbases, the truncated eigenbases, which you take to act over here and update your T. So this old T maps to new T. And you keep doing this, like CNT, 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 until you converge. Is this making sense? It's a simple algorithm to implement. It's quite neat. Oh yeah, I forgot to put the references. It's also quite old. It's from the 90s. Yeah, so that's the number that we have, and we want to optimize this number. We want ground states. So PEPS are used for ground states. We want the lowest energy state. The Hamiltonian is Hermitian, so we just want to minimize the expectation value of the energy. Initially, we had this stuff. It's called numerical gradients. It's essentially approximate gradients. The first important one was the finite difference. This was never practically used, but it was good to see that gradient descent is the thing that we need. So we were doing imaginary time evolution first, because that's easier to implement. But this apparently completely misses the mark. Like your energies are worse, and your physical properties of the state that you get are just wrong. So there was something wrong with that. But with the very expensive, if you just do it and do a finite difference gradient descent on some sort of a PEPS for a certain Hamiltonian, you see, okay, no, this really is the thing. So people came up with approximate gradients. Those are these guys. They were horrible to implement. Really, like this was the bulk of your worry in making a PEPS code would be this thing. Calculating a gradient was awful, and hence no one was entering the field. The entrance bar became so high. It was just 2 or 3 people doing this, and that's it. So we were all very happy when automatic gradients migrated over from the machine learning community, where essentially if you're able to calculate a cost function, which we easily can, right? I just told you how to calculate the cost function, and you do this in Python or whichever one where there is a standard AD library, you can just get the gradient, and all the worries from before are over, and life can be good, you know? So this was the promise, this was the dream. Yeah, so let's see what this would do. So that's your energy. The C and T, implicitly they depend on your PEPS tensor, right? So you have to go back through all of the iterations that you did to find C and T, and this can be quite a lot of them. So there are 3 problems with just this thing as I described it. So it's costly in memory. You have to store all of these old iterations. Very memory intensive. So that's no good. The gradient of the eigendecomposition. So I told you this enlarged corner, right? You need to do an eigendecomposition of this thing, or in a slightly different version of CTM, there's an SVD that you have to do. This is very poorly conditioned. We will see the formula for the gradient later. There's a 1 over the difference in eigenvalues. So if your eigenvalues get close together or the same, then it even is poorly defined. It's just not defined. So that's a problem. And then most importantly, what people thought was a perfectly working black box that will give you a gradient was actually not a perfectly working black box. And it didn't actually give an exact gradient. The problem is that the gradient for the eigenvalue decomposition that was given looked complicated enough that you wouldn't check it, but it did happen to be wrong. And so for years, yeah, I guess a couple of years, since this thing was introduced, people have been running their PEPS code with this AD, running into problems, and essentially been misdiagnosing this problem number 3, for the second problem. People have been very worried about these degenerate spectra, thinking, okay, that's really an issue. while actually we set out to solve this problem. And then in doing so, we found, okay, if we dig a little into this toolbox, we find that the gradient is just wrong. And so it's very normal that you run into problems. Yeah, so we solve all of these things. I will quickly run. Do I have to be very quick? I'll try to be very quick. Yeah, let's go through the solutions. So this was the starting point for the incorrect gradient. So it's assumed that your eigendecomposition or your SVD is just this. But you have to remember the right-hand side is rank deficient. So it assumes, it assumes that M itself is rank deficient. And so this is an exact eigendecomposition that you made, which is of course not the case. You made a truncation. So there's this missing part that was not included. And if you include it, yeah, then you get a slightly different equation for dP, so the variation of the isometries. And you get exactly the same story in SVD. There's just a missing term in the beginning of the derivation, and then you push it all the way to the end, and you get to an equation that looks fairly complicated, but it's missing a term. Yeah, so we include it, and then everything works fine. And the wonderful thing that we found is, so all of this stuff, you're very happy that you don't have to calculate it. So you discard this spectrum. This can really be most of the spectrum by really an order of magnitude. So you're quite happy not to have to calculate this thing. And you would think, okay, if you want to differentiate it, that you would maybe have to calculate it. But the thing is, that's just not. So a projection onto P orthogonal over here can be easily represented with 1 minus a projection on the space that you keep. Yeah, okay, good. So this is also the part that would be potentially relevant in a backwards kind of way. So we get AD from the machine learning people, and then, okay, we fix a bug in the eigendecomposition, and then we hand it back, and hopefully if ever anyone is using AD on a truncated decomposition, they know now to use a different formula, which is nice. The divergences, this had a bit of a complicated solution. We change our CTM with an extra step. So after doing our eigendecomposition, so you have your enlarged corner, you do the eigendecomposition. Then we add an extra step that we multiply with a Q, just an arbitrary Q. You know, just imagine it should be a unitary, but any unitary will do. So it's essentially just a rotation. So this thing is now no longer diagonal. And you also put this Q over there. And then this new CTM algorithm will also just work. And it will actually give you the same result, but everything is sort of transformed like this. So you get Qs everywhere. But you see that these Qs in the energy, let me quickly go back up. In the energy, if you put a Q and a Q dagger here on this bond, yeah, they cancel. So it's a gauge transform. So the Qs that you introduce in this CTM, they don't end up changing the energy. And so dq can be whatever we want. So in this differentiation that you would be doing, the backwards differentiation, you have this freedom to say like, maybe my gradient is divergent, but I can make dq also divergent in a negative way. And so I just cancel the divergence, which turns out to be possible. So in regular CTM, you get this thing for your gradient. So P dagger dP has this inverse difference in eigenvalues happening over there. And DC is diagonal. And then if you introduce this Q thing, and you don't even have to change your CTM, right? You can run CTM with Q equal 1. So it's not doing anything. But you can make dq, you can choose it just such that all the divergences pop away. And then your DC becomes non-diagonal, and this thing becomes 0. So what used to be problematic and divergent can now just be dropped entirely. So that's quite a pleasing.
Quick question.
Yeah.
The Ci and Cj, they are the eigenvalues of C?
Yes.
Okay.
C actually is the eigenvalues.
Okay. C is diagonal.
Yes.
In the classical,
it would be the eigenvalues of
yeah, it comes back to this thing here. Okay.
this thing. So M is your enlarged corner, and C, if you want to call it eigenvalues, would be the eigenvalues of this thing, and you truncate them.
Yeah, because the C at the left and the right part of this equation aren't necessarily the same, right? It's just your.
They are the same.
They are here.
But you have a wiggly line, so it's not equal.
Yeah, but I don't see why C would be diagonal though. Why do you assume that C is diagonal then?
Because this is an eigendecomposition.
Of what?
Of this thing.
But why in this thing would C be diagonal?
So this is so C on both sides must be the same to be converged.
So I remember that you said that this system is Hermitian. So CTT, they are Hermitian. So I don't. Okay. So I have the same question as Guillaume. So I didn't convince that why C in the left is the same thing as C in the right.
Oh, it's like if you put in random C's and T's, it's not gonna be. This is the special C that has been converged. So you run the CTM and you want the special C and the special T that has this property.
So this is more like an assumption on your parameterization. So you're assuming that you're parameterizing your model. So you're putting a constraint, right? So C has to be diagonal from the beginning, basically. So another way to see it is, let's say you take any PEPS where you have C and T that are arbitrary, right? Then it's not necessarily true that there exists a reparametrization, like a gauge or something like this, that makes C diagonal.
Yes, it is. Like so the PEPS is given, and T and C are completely fixed by the PEPS. So that these things are not free. So they definitely satisfy the fixed point condition, where the T and the C associated to this PEPS must have that if you calculate this thing and you do truncated eigendecomposition, this is your truncated eigendecomposition.
Okay.
And
but even in the left-hand side, you already have that, right? It's because of properties of this infinite thing that you're evolving, like doing this infinite contraction, that it converges to this. Okay, I see.
Yeah.
So C
like let's say you start with a non-diagonal C. After one iteration of the CTM, it will be diagonal, because C is it just you just keep it as the spectrum of the previous step. So it's not a condition. It's kind of that's just how the iterating thing would work.
Okay.
But if
it's also the case that if you go from I think it's the previous slide where you had your first PEPS, because what defines the PEPS is this A and B tensor, basically, right? And from that, it's like the idea is that if you start to make them go to the infinity, you will necessarily see this T and C appears, where C is diagonal.
Yes. Yes. So yes. So C and T are the thing you can put at the infinite boundary that you can move inward. And so it's fully determined by the PEPS, and it's a very special property that it can like move inward.
Okay, so I think I see. It's like the same thing if you do that on an MPS, like if you start to iterating your transfer operator, at some point it converges with something and you can make an eigendecomposition of this thing. And this is where this diagonal thing will appear in the middle, basically, right? I mean, we can maybe
similar. It's a power method. Yeah. Like
okay. I think I kind of see it.
It would be like
to write it down.
If you have an infinite MPS, then you would look for the thing you would put at infinity would be the fixed point vector of the transfer matrix. But in this case, the fixed point vector needs to be generalized to a boundary that fully envelops the boundary of the PEPS. Yeah. And so it's no longer like a nice eigenvalue equation. It's this CTM kind of thing.
Okay, I see.
Yeah.
Thank you.
Nice. Thank you, indeed. Okay. There we go. So with the Q deformation, and then we got rid of the divergent part, which was to us very pleasing. We were hoping to soften the problem, but it's just making it 0 is it seems like more than you should be able to get out. But yeah. Good. And then finally, the iterations, they kind of have a known solution, which I'm sure you guys would know, is the fixed point differentiation. So instead of differentiating the power method, you would say, well, actually my solution is given by this equation. So let's just differentiate that. And so then you end up with this kind of a thing, which is a linear problem. So that's the known solution. So even the early people working on AD knew fixed point equations can be treated like this, and you can use the AD toolbox to calculate this stuff as well. So this is just one backwards iteration step that you have to solve a linear problem with. However, we don't actually have a nice fixed point equation because this x really has to be the same x. But we don't have that thing happening because an eigendecomposition or an SVD is not exact. It's not unique. So all eigenvectors can be given random phases, right? And they can be given independent random phases. So any sigma over here that is diagonal will automatically commute and cancel. So this u times sigma is an equally valid eigendecomposition as this u. And so our tensors, our C and T tensors, have this random freedom in there, which, okay, is important to realize. And so, okay, the point is realize this and then gauge fix it, and then you can do this thing, which we do, and it works very well. Okay, do I have time still?
How much more?
1, essentially.
Yeah, sure, go ahead.
Okay. So we compare, we check it with a state. So we have an SU2 symmetric state. So it's an RVB, nearest neighbor RVB, some long range RVB, and some SU2 symmetry breaking part of it. Because we want to see the effect of the degeneracies in the spectrum, right? So if you have SU2 symmetry, you will have these EREPs appearing in the eigenspectrum. So you will have many degeneracies. And we want to see the effect of having the degeneracy and lightly breaking the degeneracy and see what this will do. We chose a random Hamiltonian because you do need to calculate an energy of something, and then a gradient. And the result is as follows. So the green line is if you don't take dp into account at all, which happens to be, this was one of those early self-implemented approximate gradients. They didn't know that this was what they were doing, but you end up essentially doing AD without taking dp into account. So then you get this, which is reasonable. You know, it will give you something and you can do some optimizing. But you can also see why that you can only go so far with this technique. The warm colors are the current AD. So they have the wrong equation for dp, right? There was a missing term. And so you see they're really performing, surprisingly poorly, really. There is epsilon in the x-axis, and that's the epsilon introduced to treat the degeneracy. So you had this f in the gradient appearing, and you do this Lorentzian broadening. You essentially just remove the divergence. So epsilon is some small number ranging from 10 to the minus 15 to 10 to the minus 5. And you kind of soften the divergence, but the bigger the epsilon you put in, the farther you deviate from the actual formula. So it's a bit of a trade-off, and you want to see how the trade-off works. So you see, weirdly, exact degeneracy performed the best intermediate degeneracy was by far the worst, and then just not really degenerate is sort of in the middle. So it's a weird thing where people thought degeneracies were really the issue, and we're trying to solve this, which is why we started this project. And then you see that actually degeneracies, they come out the best. This you want the degeneracies. But the problem that people tried, I mean, it's a misdiagnosis, right? They thought they had the right gradient, but they didn't. So then if you do the cold colors, this is AD without using this trick with a Q that eliminates this divergence. So there is still an epsilon dependence. And over here as well, you can see the complete degeneracy performs best. So this does really quite well. Intermediate, the worst, it completely jumps up, and then no degeneracy does okay. So you see that even with an exact, like with a proper AD, but you kind of have to do something with these degeneracies, you still see some effect for not having done the Q trick. Yeah. And we compared, just to be clear, like all of this is compared to R gradient, which we assume to be exact, and we checked R gradient to fourth or fifth order finite difference. It really came out to be the correct gradient. Yeah, good. So the lesson for us really is AD for PEPS. It's nice, it's great, but you should be careful with black boxes, and you should know what your code is doing, and just blindly using this stuff is dangerous. Yeah. But with this, we very much expect that the great bright tomorrow for PEPS that should have started when the first people introduced AD for PEPS, it should start around now, because now we do have a proper gradient and it is easy to use PEPS now. So we're very excited. And with that, I thank you.
Bram, the great talk.
Yeah, thank you.
Thank you.
Thank you very much.
Do you have some some code, some libraries online where you fix the, how did you do it? Did you kind of push or commit some kind of changes to existing libraries, or are you developing your own? Like, for what is the status right now? If I want to do correct AD for this truncated eigen decomposition, should I just look at the equation and correct it myself in the code, or is there something out there that I can use?
So we have an appendix in which we, so if you're doing AD, the formula for the derivative doesn't work, right? You want to backpropagate. And the backpropagation is actually not super trivial, because right. So here you see, like, giving dp as a function of dm is not trivial, right? It's right? You need to solve like a linear problem. And so also for the backpropagation, you need to solve a linear problem for your adjoints. So it's not a trivial analysis, but we do give it, and we give the solution. So if you you should be able to make the custom backpropagation of SVD and just plug in the formulas that we have. We do have a a fresh PhD student who's implementing a PEPS code that is supposed to be published online, but it's not yet happened. And this one will have all the proper stuff in there. Also, the code, Julia code of the Ghent group by Jito Hageman is already very good. So they have the AD stuff implemented also for complex numbers. And I imagine they would have patched their SVD probably already, because they were aware, like we were in contact, but they held off from doing it publicly.
But like in all the libraries that machine learners are using daily, like PyTorch, JAX, and the like, this is still implemented incorrectly, right? So basically what you're saying is every time you start to truncate this eigendecomposition, so the exact eigendecomposition is correctly implemented, right? So if you just do
Yes.
eigendecomposition, backprop through it in Torch or JAX or whatever, then this works correctly. But as soon as you start to assuming that truncated, the output will be in your forward pass will actually be correctly repercuted in the backward, it's not.
It's not.
Because there is this
Indeed.
term that is missing. Yeah, okay.
Indeed. Although, so the people that I know that did it in Python did have to write their own backpropagation for the truncated SVD. So I don't think so. The function you need to call to do a truncated SVD, I don't think has a standard backpropagation.
No, so you can call the SVD, then truncate, but you should know that here it's not.
Indeed, if
you
you're doing a full SVD and then truncating, that is perfectly possible to backpropagate. That's completely fine.
I see. Here is because you don't do the full SVD.
Indeed. If you refrain from ever, and it's a lot, right? Because the number of eigenvalues that you want to keep is something like the order of the bond dimension, but the number that there is bond dimension of your environment times PEPS dimension squared.
Yeah.
So it's really way more. So you really don't want to do that.
Okay, I get it. Okay, thanks. Okay.
So I had a really tangential question.
Yeah, please.
You briefly mentioned at some point that some people are working on using an MPS for Navier-Stokes. Do you have a reference for that? I've recently become interested by that kind of stuff.
Yeah, Dieter. It's a Russian name.
Well, thanks for being there, Guillaume. I guess you can probably end the recording now anyways, given that the talk is over. So